Dr. Engineering Thermodynamics, Assistant Professor. SRM Institute of Science and Technology. Third Law of Thermodynamics and Entropy. Limitations of Second Law of Thermodynamics. Explanation of the concept of entropy. Clausius inequality, TS diagram. Entropy change for different processes. Principle of increase of entropy, PVT behavior and properties of ideal gas mixtures. Dalton's law of partial pressures, Avogadro's law. Gibbs-Dalton law, enthalpy and specific heat of a gas mixture. Maxwell relations, TdS equations, difference and ratio of heat capacities. Energy equation, Joule Thomson coefficient, Clausius-Clapeyron equation. Entropy change of ideal and real gases. Isentropic efficiencies of steady flow devices. Exergy high and low grade energy. Available and unavailable energy of a source and finite body. Limitations of thermodynamics is a concept that limits the occurrence of many processes that, despite being permitted by other physical laws. For instance, water in a glass that is at ambient temperature never spontaneously cools to create ice cubes, which would release energy into the environment. When everything is at the same temperature, there can be no work done and all of the energy is squandered as random atom and molecule motion, which is the most extreme level of disorder. Applies only to macroscopic systems. Does not predict rate of processes. Assumes ideal or reversible processes. Cannot predict equilibrium state from initial conditions. The level can be viewed as a measure of molecular disorder of a substance or molecular randomness as it melts or evaporates. The entropy of a substance is lowest in the solid phase and highest in the gas phase. As a system becomes more disordered, the positions of the molecules become less predictable and the entropy increases. Gas phase is associated with the molecular chaos. In gaseous phase is a high value of entropy. The entropy of a system is related to the total number of possible microscopic states of that system, called thermodynamic probability P, by the Boltzmann relation, expressed as S equals K ln P, where K equals 1.3806 10 to 23 J/K is the Boltzmann constant. Therefore, from a microscopic point of view, the entropy of a system increases whenever the molecular randomness or uncertainty, i.e., molecular probability, of a system increases. The molecules of a substance in solid phase continually oscillate, creating an uncertainty about their position. These oscillations, however, fade as the temperature is decreased, and the molecules supposedly become motionless at absolute zero. This represents a state of ultimate molecular order, and minimum energy. Therefore, thermodynamics at absolute zero temperature is at absolute zero temperature is zero since there is no uncertainty about the state of the molecules at that instant, Fig. This statement is known as the third law of thermodynamics. The third law of thermodynamics provides an absolute reference point for the determination of entropy. The entropy determined relative to this point is called absolute entropy, and it is extremely useful in the thermodynamic analysis of chemical reactions. In the absence of any friction, raising a weight by a rotating shaft does not create any disorder or a flywheel. Entropy does not produce any is not degraded during this process. Any process that does not produce a net entropy is reversible, and thus the process just described can be reversed by lowering the weight. The paddle will work in a gas with increases the level of disorder of the gas entropy as evidenced by a rise in gas temperature is degraded creating a higher level of molecular disorder in the container. Only a portion of this energy can be converted to work by partially reorganizing it through the use of a heat engine. Therefore, energy is degraded during this process, the ability to do work is reduced, molecular disorder is produced, and associated with all this is an increase in entropy. The quantity of energy is always preserved during an actual process, the first law, but the quality is bound to decrease, the second law. This decrease in quality is always accompanied by an increase in entropy. The entropy and the level of molecular disorder or randomness of the hot body decreases with the entropy and the level of molecular disorder of the cold body increases. During a heat transfer process, the increase in entropy of the cold body be greater than the decrease in entropy of the hot body, cold body more than the net entropy of the combined entropy of the hot body. The cold body and the hot body increases. That is, the combined system is at a state of greater disorder at the final state. Thus we can conclude that processes can occur only in the direction of increased overall entropy or molecular disorder. Entropy generation can be viewed as a measure of disorder or disorganization generated during thermodynamics. Efficient people lead low entropy, highly organized lives. People leading high entropy lifestyles are always on the run, and never seem to catch up. Some people seem to learn fast and remember well what they learn. We can call this type of learning organized or low entropy learning. A library with a good shelving and indexing in the workplace is viewed as a low entropy library because of the high level of organization. Having a disorganized, high entropy army is like having no army at all. Mechanical friction is always accompanied by entropy generation, and thus reduced performance. Irreversibilities such as combustion, friction, mixing, chemical reactions, heat transfer through a finite temperature difference, unrestrained expansion, non-quasi-equilibrium, compression, or expansion always cause the entropy of a system to increase, and entropy generation is a measure of the entropy created by such effects during a process. For a reversible process, a process that involves no irreversibilities, the entropy generation is zero and thus the entropy change of a system equals the entropy transfer. The entropy transfer by heat Q/T is zero for adiabatic systems, and the entropy transfer by mass Ms is zero for systems that involve no mass flow across their boundary, i.e., closed systems. Entropy balance for any system undergoing any process. Or, in the rate form, as where the rates of entropy transfer by heat transferred at a rate of q degree and mass flowing at a rate of m degree r. S degree heat equals q degree/T. S degree mass equals m degree S. The entropy balance can also be expressed on a unit mass basis as where all the quantities are expressed per unit mass of the system. For a reversible process, the entropy generation terms gen drops out from all of the relations above. The terms gen represents the entropy generation within the system boundary only. Mechanisms gen represents the entropy generation within the system boundary only, Fig, and not the entropy generation that may occur outside the system boundary during the process as a result of external irreversibilities. Therefore, a process for which gen equals 0 is internally reversible, but not necessarily totally reversible. Entropy generation outside during a process can be determined by applying an entropy balance on an extended system that includes the system and its immediate surroundings where external irreversibilities might be occurring. Also, the entropy change in this case is equal to the sum of the entropy change of the system and the entropy change of the immediate surroundings. The entropy change of a system during a process is greater than the entropy transfer by an amount equal to the entropy generated during the process within the system, and the increase of entropy principle for any system is expressed as the entropy balance relation above can be stated as the entropy change of a system during a process is equal to the net entropy transfer through the system boundary and the entropy generated within the system. The entropy balance relation above can be stated as the entropy change of a closed system during a process is equal to the sum of the net entropy transferred through the system boundary by heat transfer and the entropy generated within the system boundaries. For an adiabatic process, Q equals 0, the entropy change of the closed system becomes equal to the entropy generation within the system boundaries. Any closed system and its surroundings can be treated as an adiabatic system, and the total entropy change of a system is equal to the sum of the entropy changes of its parts. The entropy balance for a closed system and its surroundings can be written as where system equals m, S2, S1, and the entropy change of the surroundings can be determined from SIR equals XIR/SIR if its temperature is constant. Control volumes. The entropy balance relations for control volumes differ from those for closed systems in that they involve one more mechanism of entropy exchange, mass flow across the boundaries. The entropy of the control volume changes as a result of mass flow as well as heat balance relations be expressed for control volumes as, or, in the rate form, as. This entropy balance relation can be stated as the rate of entropy change within the control volume during a process is equal to the sum of the rate of entropy transfer through the control volume boundary by heat transfer, the net rate of entropy transfer into the control volume by mass flow, and the rate of entropy generation within the boundaries of the control volume as a result of irreversibilities. The entropy of a substance encountered in practice such as or remains constant in the case of a reversible process compressors as it flows through a single stream, adiabatic, steady flow exchangers, pipes, and ducts operate steadily, and thus they experience no change in their entropy. For single stream, one inlet and one exit, steady flow devices, the entropy balance relation simplifies to. For the case of an adiabatic single-stream device, the entropy balance relation further simplifies to, which indicates that the specific entropy of the fluid must increase as it flows through an adiabatic device since G greater than or equal to 0. If the flow through the device is reversible and adiabatic, then the entropy remains constant, Se equals Si, regardless of the changes in other properties. Clausius inequality. The cyclic integral of delta Q/T is always less than or equal to 0. This inequality is valid for all cycles, reversible or irreversible. Any heat transfer to or from a system can be considered to consist of differential amounts of heat transfer. Then the cyclic integral of dQ/T can be viewed as the sum of all these differential amounts of heat transfer divided by the temperature at the boundary. To demonstrate the validity of the Clausius inequality, consider a system connected to a thermal energy reservoir at a constant thermodynamic, i.e., absolute, temperature of Tr through a reversible cyclic device, Fig. Applying the energy balance to the combined system identified by dashed lines yields. Where delta Wc is the total work of the combined system, Re plus delta Wsys, and dec is the change in the total energy of the combined system. Considering that the cyclic device is a reversible one, we have where the sign of delta Q is determined with respect to the system, positive if to the system and negative if from the system. Eliminating delta Qr from the two relations. Let the system undergo a cycle while the cyclic device undergoes an integral number of cycles. Then the preceding relation becomes. It appears that the combined system is exchanging heat with a single thermal energy reservoir while involving, producing or consuming, work Wc during a cycle. On the basis of the Kelvin-Planck statement of the second law, which states that no system can produce a net amount of work while operating in a cycle and exchanging heat with a single thermal energy reservoir. Wc cannot be a work output, and thus it cannot be a positive quantity. Considering that Tr is the thermodynamic temperature and thus a positive quantity, we must have, which is the Clausius inequality. This inequality is valid for all thermodynamic cycles, reversible or irreversible, including the refrigeration cycles. If no irreversibilities occur within the system as well as the reversible cyclic device, then the cycle undergone by the combined system is internally reversible. As such, it can be reversed. In the reverse cycle case, all the quantities have the same magnitude but the opposite sign. Therefore, the work Wc, which could not be a positive quantity in the regular case, cannot be a negative quantity in the reversed case. Then it follows that Wc int rev equals 0 since it cannot be a positive or negative quantity, and therefore, for internally reversible cycles. Thus, we conclude that the equality in the Clausius inequality holds for totally or just internally reversible cycles and the inequality for the irreversible ones. Now consider the volume occupied by a gas in a piston, cylinder device undergoing a cycle. When the piston returns to its initial position at the end of a cycle, the volume of the gas also returns to its initial value. Thus the net change in volume during a cycle is zero. This is also expressed as the cyclic integral of volume, or any other property, is zero. Conversely, a quantity whose cyclic integral is zero depends on the state only and not the process path, and thus it is a property. Therefore, the quantity, dq/t, int rev must represent a property in the differential form. Is designated S and is defined as. Entropy is an extensive property of a system and sometimes is referred to as total entropy. Entropy per unit mass, designated S, is an intensive property and has the unit kJ/kgk. The entropy change of a system during a process can be determined by integrating above EQ between the initial and the final states. Engineers are usually concerned with the changes in entropy. Therefore, the entropy of a substance can be assigned a zero value at some arbitrarily selected reference state, and the entropy values at other states can be determined. Note that entropy change between two specified states, like all other properties, it has fixed values reversible or irreversible. Therefore, the entropy change between two specified states is the same no matter what path, reversible or irreversible. Consider a cycle that is made up of two processes, process 1 to 2, which is arbitrary, reversible or irreversible, and process 2 to 1, which is internally reversible, as shown in figure. From the Clausius inequality. The second integral in the previous relation is recognized as the entropy change S1, S2. It can also be expressed in differential form as, where the equality holds for an internally reversible process and the inequality for an irreversible process. The quantity delta S equals S2, S1 represents the entropy change of the system. For a reversible process, it becomes equal to 12 indefinite integral dq/t, which represents the entropy transfer with heat. The inequality sign in the preceding relations is a constant reminder that the entropy change of a closed system during an irreversible process is always greater than the entropy transfer. That is, some entropy is generated or created during an irreversible process, and this generation is due entirely to the presence of irreversibilities. The entropy generated during a process is called entropy generation and is denoted by Sgen. Noting that the difference between the entropy change of a closed system and the entropy transfer is equal to entropy generation, EQ, can be rewritten as an equality as. Note that the entropy generation Sgen is always a positive quantity or zero. Its value depends on the process, and thus it is not a property of the system. Also, in the absence of any entropy transfer, the entropy change of a system is equal to the entropy generation. Equation has far-reaching implications in thermodynamics. For an isolated system, or simply an adiabatic closed system, the heat transfer is zero. This equation can be expressed as the entropy of an isolated system during a process always increases or, in the limiting case of a reversible process, remains constant. In other words, it never decreases. This is known as the increase of entropy principle. Note that in the absence of any heat transfer, entropy change is due to irreversibilities only, and their effect is always to increase entropy. The differential form of the conservation of energy equation for a closed stationary system, a fixed mass, containing a simple compressible substance can be expressed for an internally reversible process as. The second TdS equation is obtained by eliminating do by using the definition of enthalpy, H equals U plus PV. H equals U plus PV rightward arrow dH equals do plus PdV plus VdP. TdS equals do plus PdV. TdS equals dH, VdP. Relates entropy changes of a system to the changes in other properties. The TdS relations are valid for both reversible and irreversible processes and for both closed and open systems. From the above TdS relations, the entropy change during a process can be determined by integrating either of these equations between the initial and the final states. To perform these integrations, do equals CV dt and dH equals Cp dt for ideal gases, as well as the equation of state for the substance, such as the ideal gas equation of state PV equals RT. An expression for the ideal change of an ideal gas can be obtained from substituting do equals Cv dt and P equals RT/V in 1. The entropy change for a process is obtained by integrating this relation between the end states. Substituting dH equals Cp dt and V equals RT/P in 2. The specific heats of ideal gases, with the exception of monatomic gases, depend on temperature. Entropy change of liquids can be approximated as incompressible substances since their specific volumes remain nearly constant during a process. Since Cp equals Cv equals C and do equals C dt for incompressible substances, the entropy change for liquids and solids during a process is determined by the entropy change of a truly incompressible substance depends on temperature only and is independent of pressure. A relation for isentropic processes of liquids and solids is obtained by setting the entropy change relation above equal to 0. The temperature of a truly incompressible substance remains constant during an isentropic process. To determine the properties of a mixture, mass and mole fractions, we need to know the composition of the mixture as well as the properties of the individual components. There are two ways to describe the composition of a mixture, either by specifying the number of moles of each component, called molar analysis, or by specifying the mass of each component, called gravimetric analysis. The ratio of the mass of a component to the mass of the mixture is called the mass fraction phi, and the ratio of the mole number of a component to the mole number of the mixture is called the mole fraction Y. An ideal gas is defined as a gas whose molecules are spaced far apart so that the behavior of a molecule is not influenced by the presence of other molecules' low densities. Real gases approximate this behavior closely when they are at a low pressure or high temperature relative to their critical point values. The PVT behavior of an ideal gas is expressed by the simple relation PV equals RT, which is called the ideal gas equation of state. The PVT behavior of real gases is expressed by more complex equations of state or by PV equals ZRT, where Z is the compressibility factor. Dalton's law of additive pressures for a mixture of two ideal gases is usually based on two models: Dalton's law of additive pressures and Avogadro's law of additive volumes. Dalton's law of additive pressures: the pressure of a gas mixture is equal to the sum of the pressures each gas would exert if it existed alone at the mixture temperature and volume. Avogadro's law of additive volumes: the volume of a gas mixture is equal to the sum of the volumes each gas would occupy if it existed alone at the mixture temperature and pressure. Dalton's and Avogadro's laws hold exactly for ideal gas mixtures, but only approximately for real gas mixtures. This is due to intermolecular forces that may be significant for real gases at high densities. Avogadro's law of additive volumes for a mixture of two ideal gases. For ideal gases, these two laws are identical and give identical results. Pi is called the component pressure and 6 is called the component volume. 6 is the volume a component would occupy if it existed alone at Tm and Pm, not the actual volume occupied by the component in the mixture. The ratio Pi/Pm is called the pressure fraction and the ratio 6/Vm is called the volume fraction of component I. Ideal gas mixtures Pi and 6 can be related to Y by using the ideal gas relation for both the components and the gas mixture. Is strictly valid for ideal gas mixtures since it is derived by assuming ideal gas behavior for the gas mixture and each of its components. The quantity Ypm is called the partial pressure, identical to the component pressure for ideal gases, and the quantity Yvm is called the partial volume, identical to the component volume for ideal gases. For an ideal gas mixture, the mole fraction, the pressure fraction, and the volume fraction of a component are identical. The composition of an ideal gas mixture, such as the exhaust gases leaving a combustion chamber, is frequently determined by a volumetric analysis, called the Orsat analysis. A sample gas at a known volume, pressure, and temperature is passed into a vessel containing reagents that absorb one of the gases. The volume of the remaining gas is then measured at the original pressure and temperature. The ratio of the reduction in volume to the original volume, volume fraction, represents the mole fraction of that particular gas. Let us consider a volume of a gaseous mixture at a temperature T, consisting of three constituents A, B and C. Let us further assume that each of the constituents is compressed to a pressure P equal to the total pressure of the mixture, and let the temperature remain constant. The partial volumes then occupied by the constituents will be VA, VB, and VC. Volumetric analysis of a gas mixture. Thus, the volume of a mixture of gases is equal to the sum of the volumes of the individual constituents when each exists alone at the pressure and temperature of the mixture. This is the statement of another empirical law, the law of partial volumes, sometimes called Amagas' law or Leduc's law. According to Avogadro's law, the number of moles of any gas is proportional to the volume of the gas at a given pressure and temperature. Referring to Fig. A, the volume V contains n moles of the mixture at P and T. In Fig. B, the gas A occupies a volume VA at P and T, and this volume contains Na moles. Similarly, there are Nb moles of gas B in volume VB and Nc moles of gas C in volume VC. Volumetric analysis of a gas mixture. Avogadro's law, VA plus VB plus VC equals V. The total number of moles in the vessel must equal the sum of the moles of the individual constituents. N equals Na plus Nb plus Nc equals sigma Ni. Dalton's law was reformulated by Gibbs to include a second statement on the properties of mixtures. The combined statement is known as the Gibbs-Dalton law, and is as follows. The internal energy, enthalpy, and entropy of a gaseous mixture are respectively equal to the sums of the internal energies, enthalpies, and entropies, of the constituents. Each constituent has that internal energy, enthalpy, and entropy, which it could have if it occupied alone that volume occupied by the mixture at the temperature of the mixture. Gibbs-Dalton law. The Maxwell relations that relate the partial derivatives of properties P, V, T, and S of a simple compressible system to each other are called the Maxwell relations. They are obtained from the four Gibbs equations. From TdS relation. W.K.T. The other two Gibbs relations are based on two new combination properties, the Helmholtz function A and the Gibbs function G, defined as differentiating, we get. Simplifying. The four Gibbs relations are in the form dz equals mdx plus ndy. With since U, H, A, and G are properties and thus have exact differentials. Applying above equation to each of them. These are called the Maxwell relations. They are extremely valuable in thermodynamics because they provide a means of determining the change in entropy, which cannot be measured directly, by simply measuring the changes in properties P, V, and T. The specific heats of an ideal gas depend on temperature only. For a general pure substance, however, the specific heats depend on specific volume or pressure as well as the temperature. At low pressures gases behave as ideal gases, and their specific heats essentially depend on temperature only. These specific heats are called zero pressure, or ideal gas, specific heats, denoted CV equals 0 and camp equals 0, and they are relatively easier to determine. General relations that enable us to calculate the specific heats at higher pressures, or lower specific volumes, from a knowledge of CV equals 0 or camp equals 0 and the PVT behavior of the substance. The equations below yields the deviation of Cp from Cp0 with increasing pressure, for example, is determined by integrating last equation from zero pressure to any pressure P along an isothermal path. Specific heat CV and Cp. The temperature behavior of a fluid during a throttling or remain constant during a throttling process is described by the Joule Thomson coefficient, defined as the Joule Thomson coefficient is a measure of the change in temperature with pressure during a constant enthalpy process. Some constant enthalpy lines on the TP diagram pass through a point of zero slope or zero Joule Thomson coefficient. The line that passes through these points is called the inversion line, and the temperature at a point where a constant enthalpy line intersects the inversion line is called the inversion temperature. The temperature at the intersection of the P equals 0 line, ordinate, and the upper part of the inversion line is called the maximum inversion temperature. Notice that the slopes of the H equals constant lines are negative, μ0, at states to the right of the inversion line and positive, μ0, to the left of the inversion line. For hydrogen, for example, the maximum inversion temperature is 68 degrees Celsius. Thus hydrogen must be cooled below this temperature if any further cooling is to be achieved by throttling. A general relation for the Joule Thomson coefficient in terms of the specific heats, pressure, specific volume, and temperature. For an H equals constant process we have dH equals 0. Thus, the Joule Thomson coefficient can be determined from a knowledge of the constant pressure specific heat and the PVT behavior of the substance. It is also possible to predict the constant pressure specific heat of a substance by using the Joule Thomson coefficient, which is relatively easy to determine, together with the PVT data for the substance. The temperature of an ideal gas remains constant during a throttling process since H equals constant and T equals constant lines on a temperature remain constant when the enthalpy remains constant. A throttling process cannot be used to lower the temperature of an ideal gas. The gases at low pressures behave as ideal gases and obey the relation PV equals RT. The properties of ideal gases are relatively easy to evaluate since the properties U, H, Cv, and Cp depend on temperature only. At high pressures, however, gases deviate considerably from ideal gas behavior. It enables us to determine the enthalpy change associated with a phase change, such as the enthalpy of vaporization HFG, from a knowledge of P, V, and T data alone. Consider the third Maxwell relation. The slope of the saturation curve on a P phase diagram is constant at a constant T or P. The integration yields. Or, during this process the pressure also remains constant. Therefore, substituting in above N, which is called the Clapeyron equation, it enables us to determine the enthalpy of vaporization HFG at a given temperature by simply measuring the slope of the saturation curve on a PT diagram and the specific volume of saturated liquid and saturated vapor at the given temperature. The Clapeyron equation is applicable to any phase change process that occurs at constant temperature and pressure. It can be expressed in a general form as, where the subscripts 1 and 2 indicate the two phases. Internal energy changes. For internal energy, using the definition of Cv, we have, substituting this into the TdS relation do equals TdS, PdV yields. Internal energy changes. Internal energy changes of dT and dV in do. Using the third Maxwell relation. Therefore, internal energy of a simple compressible system associated with a change of state from T1, V1, to T2, V2, is determined by integration. Using the definition of Cp. Also from total differential. TdS relation dH equals TdS plus VdP. Equating the coefficients of dt and dP. Using the fourth Maxwell relation. The change in enthalpy of a simple compressible system associated with a change of state from T1, P1, to T2, P2. Two general relations for the entropy change of a simple compressible system. The entropy to be a function of T and V, that is, S equals S, T, V, and take its total differential. Is the maximum useful work that could be obtained from the system at a given state in a specified environment. It would be very desirable to have a property to enable us to determine the useful work potential of a given amount of energy at some specified state. This property is exergy, which is also called the availability or available energy. The work potential of the energy contained in a system at a specified state is simply the maximum useful work that can be obtained from the system. A system that is in equilibrium with its environment is thermodynamic equilibrium with the environment it is in. A system that is in equilibrium with its environment is said to be at the dead environment, in thermal and mechanical equilibrium. It has no kinetic or potential energy relative to the environment, zero velocity and zero elevation above a reference level, and it does not react with the environment, chemically inert. Also, there are no unbalanced magnetic, electrical, and surface tension effects between the system and its surroundings. The properties of a system at the dead state are denoted by subscript 0, for example, P0, T0, H0, U0, and S0. A system has zero exergy at the dead state. No work can be produced from a tremendous amount of energy at the dead state, but no exergy. The atmosphere around us contains a tremendous amount of energy. However, the atmosphere is in the dead state, and the energy it contains has no work potential. A system delivers the maximum possible work as it undergoes a reversible process from the specified initial state to the state of its environment, that is, the dead state. This represents the useful work potential of the system at the specified state and is called exergy. Exergy does not represent the amount of work that a work-producing device will actually deliver upon installation. Rather, it represents the upper limit on the amount of work a device can deliver without violating any thermodynamic laws. The exergy of a system at a specified state depends on the conditions of the environment, the dead state, as well as the properties of the system. Therefore, exergy is a property of the system, environment combination and not of the system alone. The property exergy is the work potential of a system in a specified environment and represents the maximum amount of useful work that can be obtained as the system is brought to equilibrium with the environment. Unlike energy, the value of exergy depends on the state of the environment as well as the state of the system. Therefore, exergy is a combination property. The exergy of a system that is in equilibrium with its environment is zero. The state of the environment is referred to as the dead state since the system is practically dead, cannot do any work, from a thermodynamic point of view when it reaches that state. Based on the thermodynamic concepts, an energy source can be called as high-grade or low-grade, depending the ease with which it can be converted into other forms. Thus electrical energy is called a high-grade energy, as it is very easy to convert almost all of it into other energy forms such as thermal energy, say by using an electrical heater. Electrical and chemical energy are high-grade energy, because the energy is concentrated in a small space. Even a small amount of electrical and chemical energy can do a great amount of work. The molecules or particles that store these forms of energy are highly ordered and compact and thus considered as high-grade energy. High-grade energy like electricity is better used for high-grade applications like melting of metals rather than simply heating of water. Low-grade energy. Heat can still be used to do work, example of a heater boiling water, but it rapidly dissipates. The molecules, in which this kind of energy is stored, air and water molecules, are more randomly distributed than the molecules of carbon in a coal. This disordered state of the molecules and the dissipated energy are classified as low-grade energy. Naturally, high-grade energy sources are more expensive compared to low-grade energy sources. Whereas, it is not possible to convert thermal energy completely into electrical energy, typical efficiencies of thermal power plants are around 30%, hence thermal energy is called a low-grade energy. The exergy of an isolated system during a process always decreases or, in the limiting case of a reversible process, remains constant. In other words, it never increases and exergy is destroyed during an actual process. This is known as the decrease of exergy principle.